Okay, so the next speaker is Xin Zhou from Cornell University, and he will tell us about half-volume spectrum and constant mean curvature hypersurface.
Hello.
Yeah, first, thank you very much for the introduction, and I appreciate this opportunity to be here and to present some recent work. Thanks for organizing such a great meeting. I'm going to talk about half-volume spectrum. Let me start by recalling the Laplacian spectrum as a warm-up. So suppose that I'm on a Riemann manifold, closed Riemann manifold with a metric. The Laplacian eigenvalue and eigenfunctions are defined in this way. So this is a negative operator in my terminology. So this lambda k is eigenvalue and phi k is eigenfunction. If this is closed, we know that so the first one is less than. So we can order them in this way. This is a classical definition for the volume for the Laplacian spectrum, but we have a variational characterization in this way. We consider the Rayleigh quotient, so which applies to a function, such that this is the integral of gradient phi square over the manifold divided by phi square of phi, or if you want, normalize this to be 1. Phi is the W12 function on this manifold. Phi is not equal to 0. So this is a Rayleigh quotient. We know that the Rayleigh quotient is scaling invariant in the sense that for every non-negative real number, the Rayleigh quotient of lambda phi equal to R phi. So this means that the functional is invariant under this R star action. So let me denote R star as all real numbers, but not 0. So this is a multiplicative group. So this property implies that this functional is R star invariant. R star has a natural action on this W12 space. Okay, so then we can consider to take a quotient of the total space. So I want to write in this way. Let me first do a decomposition of this group as R positive. This is all positive real numbers. This is the subgroup of this multiplicative group. There are some with D2. So this D2 implies that you put a positive number into a negative number and vice versa. So this functional R reduces to the following. So let me first quotient out. I want to quotient out R star, but let me do it one by one. Now, I first quotient by R positive, and then quotient by D2. It's the same as quotient out this R star. Because it's invariant, I can write it in this way. The reason I do that is if I'm taking the first quotient, this is an infinite dimensional vector space taking out the origin. I quotient out all positive multiplications. It's actually homeomorphic to an infinite dimensional sphere. It's a unit sphere inside this Hilbert space. Actually, this space is not the same as a finite dimensional unit sphere because a finite dimensional unit sphere is not contractible, but this infinite dimensional sphere is contractible. And then we quotient out Z2. Finally, we get infinite dimensional projective space. So which says that my functional R reduces to functional from Rp infinity into non-negative numbers. With this structure, we can rewrite lambda k. Note that my lambda k is a kth eigenvalue, which I put in order way. So I can write lambda k as follows. So what I do is that I take any Rpk inside maybe k minus 1, inside this Rp infinity. And I take the maximum value. So this is equivalent class of functions inside this RPK. And I evaluate R phi. So R is R star invariant, so it totally makes sense. And then we can take the infimum over all such RPK structure in this infinite dimensional real projective space. So someone also, I think Andre tomorrow may give you a similar formula. Maybe you can also change these two planes if you want to write in a different way. You can say this is all k-dimensional plane going through this W12 space. You consider the maximum over non-zero functions. You can make the same definition. So this is the classical Laplacian spectrum. So as an analog, I want to now introduce the volume spectrum. So the earliest idea was due to Gromov and recently by Goose and Marcus Nevis on the application to millimole surfaces. The starting point is, let's see, the most important thing here, if you look for this picture, is we have a functional defined over a domain which is homeomorphic or homotopic equivalent to the infinite dimensional real projective space. We want to see whether we have a similar structure. Fortunately, I'm going to prove the following. There was a theorem. Before I state the theorem, let me introduce a terminology. So just to distinguish between the volume spectrum and Laplacian spectrum, when I talk about the volume spectrum, I'm using a manifold M with a Riemann metric G. Let's consider this space, C of M. This is all subset of M. So whose boundary? Let me assume it has n plus 1 dimensional because I'm going to talk about hypersurfaces. So n will be my dimension of the hypersurface. I consider all subsets whose boundary has finite n-dimensional Hausdorff measure. This is usually called the set of Cauchy-Pauli size. It's easy to see that this space is contractible. You can imagine that you give a Morse function, you use the level sets to contract anything way to amplitude side. It's a contractible side. We can compare this huge space to this infinite dimensional sphere because this is also a contractible space. The reason I can define spectrum, the topological reason is that I have this Z2 action. So I want to see whether I have a natural Z2 action here. Yes, we have. So this has a natural Z2 action given by any omega. You just map to its complement. This is a Z2 action. So let me call the quotient this space. Quotient, I call them B, have different names. Let me call them quotient out by Z2. So now this is just a set. I can give a weak topology. There's a natural weak topology here. This is called the flat topology. That's right. So the weak topology measures, given two sets of weak topology measures the volume bounded in between them. So that's a weak topology. Of course, this action is continuous under this weak topology. So after quotient, we still have a natural topological space. So this theorem, which says that under this Z2 action, we should see something similar to that picture, was originally due to Almgren. And recently had a reproof by Marcus and Nevis. So we can show that this space is also weakly homotopic to RP infinity. Okay. It's surprise and not surprise. Surprise is that we have a similar structure here as even in the linear space. This space has no linear structure at all. Unsurprised is that if you think of this space as S infinity, I have a D2 quotient, it should be RP infinity. So with this total space, there's no topological structure. It's hard to define any variational invariant. But under this structure, it's easy to do, because if you look at the cohomological ring of this space, under D2 coefficients, this is a polynomial ring with a single generator, lambda bar. This lambda bar lies in H1 of this space. OK, so now we have the first recipe for defining this new spectrum. We have this RP infinity structure. Right? The next important ingredient is to see what would be RPK. So there is a linear space. You have a plane. If you take the quotient, you get RPK minus 1. So what would be a similar thing here? So for that purpose, we have to introduce a so-called p-sweep pod. So given an integer p, so let me say, we say that a map phi is defined on, this is a parameter space. This is a finite dimensional parameter space. So you can imagine this as if you want this to be manifold or simplicial complex or cubical complex, whatever a good parameter space, map into this space. So we say this is a p-sweep pod. Well, this word has a history. By sweep pod, you usually mean a one sweep pod, which means like one parameter family of hypersurfaces that sweep out the whole manifold. It's kind of like we are doing X-ray scanning. And later on, people adapt these notations and generalize to any p-parameter families. So we still call them a sweep pod, even though it's not a sweep pod anymore. So we see that it's a p-sweep pod if something is satisfied. In this case, we can use a linear space. And in this case, we have to use topology. So the topological structure we use is that we pour back this lambda bar. So as I said, this lambda bar lies in H1, this cohomology of this space. Okay, that's in the first cohomology group. We do a pour back. This should be in H1 of the parameter space X. We're all using Z2 coefficients. But I take this car product up to a piece power. I require this is not 0 in H upper P. So this is a topological definition for p-sweep pod. It characterizes that it captures some p-dimensional real projective structure. So here's also like a heuristic explanation. The heuristic thing is as follows. For every p points, I call it y1 up to yp in my manifold. So you pick any p points, you allow them to repeat. And then I say I have a hypersurface that passes through all of them. So there's a parameter space, X in the parameter space. So this hypersurface, this is my phi of small x. That passes through all the points. If for any points, they can be identical to each other. We can find a hypersurface passing through all of them. Then we call them a p-sweep pod. This is a heuristic explanation. Then you may ask whether it's easy to find such a p-sweep pod, because it sounds to be a pretty restrictive requirement. It's easy if you allow them to be disconnected, which is sure. I mean, we allow them to be disconnected. You can find such parallel surfaces which cover p points. That's very easy. So the space of p-sweep pod are abundant. There are a lot of them. Okay. So this is the second ingredient comparing to this definition of lambda k. So now we have RP infinity. We have RPK. So we can make a similar definition now. Right? So we can make the definition. The P width, so we call all of them as a volume spectrum. It's defined as the following. We take an arbitrary P sweeport, and say it's a phi. And then we take the maximum, so this is their defining domain of the area. This is the n-dimensional area of this hypersurface. And then take the infimum over all possible P sweeport, and then we define them to be omega of P, which depends only on the manifold and the metric. Okay. Call them the P sweeport. I should give this definition to a number of names like Gromov, Goose, Marcus, Navis, and so on. So let me just skip that definition of the P width. From the definition, it's easy to see that this is also a sequence of monotone, non-decreasing sequence of numbers. Because by that definition, if it's a P sweeport, it's automatically a P minus 1 sweeport. So this is automatic monotone. Then you may ask, like, what further information do we know about them? There's a notable theorem, which was a conjecture of Gromov. They say that to satisfy the Weil law. It's a theorem by so they show that this sequence of numbers has a uniform asymptotics depends on the dimension, the volume, after renormalization times p to the power 1 over n plus 1. It's a sublinear type growth condition. Okay? So this is that this is usually called the Weil law. So this is about the classical volume spectrum. Today I want to talk about a variant of this, which we call the half-volume spectrum. Now let me just introduce the definition before I give you more motivations. So I consider a subspace of them, which is an invariant hypersurface under Z2 action. You can imagine like what kind of subspace I can take from this. So one thing we consider is this. C a half are all of those subsets in C of M, so which bound half of the volume. So for later purpose, allow me to write this as a small h. For later purpose, it's half of the total volume. We consider all subsets which bound half of the total volume. So this is a Z2 invariant. Or you can think of this as Z2 invariant hypersurface inside this. I mean, I couldn't say that because we don't have a strong topological structure to think about a hypersurface. But you should imagine this is a hypersurface. This is a single constraint over this huge space. So it's a Z2 invariant. Now we can consider the quotient under this Z2 action. Right? So we call them H and Z2. That's just a quotient of this under this Z2 action. So since we know Cm is contractible, this is also a contractible. It's still a contractible space quotient by Z2 action. You can imagine it's also RP infinity, and we prove that. So was here it was a proposition. This was collaborated with Liam Mazurowski. So we show that this space is also weakly homotopic to RP infinity. Okay. So with this, we can similarly generalize everything I wrote on those two boards to this new setup. For that, we introduce the definition of half-volume spectrum. So we call them omega tilde p. So let me just say, like, you define everything replacing by, so everything is the same, but with n, b replaced by this half volume cycles, half volume hypersurfaces. Call them omega tilde p. So now you can really think about we have defined what this means for an half volume p sweeport. Those are the p sweeport like p parameter family or like x parameter family of hypersurfaces, which each of them bound half of volume. It also satisfies this kind of heuristics. Under this assumption, it's easy to see that every half volume p sweeport is also a classical p sweeport. So we trivially have this comparison. And we can also show that you give arbitrary p sweeport, you can deform them sort of to half volume spectrum by paying a little bit price. So we can also show that this is true, some universal constant. Okay. Then a direct corollary of this inequality is that the Weyls law is still a base of Weyl law, because if you satisfy this asymptotics, if you add a constant, still satisfy the same asymptotics. So this also has the same Weyl law. Okay. Yeah. So I say it's a lemma, and the proof is just by this inequality. You can get that. So this is a main concept I want to introduce. And now I want to go into more geometric part, like why we're interested or what leads us to think about this new spectrum. So that has a tight connection with geometry. It has a connection with minimal surfaces and CMC surfaces, constant mean curvature, hypersurfaces. So let me give a brief introduction of the version formula related to them. So think about this as a hypersurface inside n plus 1 dimensional space. Assume that locally has a unit normal vector field n. If you have arbitrary ambient vector field x, which is a vector field in M, so we can do the first variation argument. So this means that I take the first derivative of the area if I perturb this hypersurface along the direction of x. So it only depends on the vector field and the surface. So it will become the mean curvature times the normal speed. Okay. So if h is 0 everywhere, that implies that it's a critical point for the area functional. So sigma is called a minimal hypersurface. Okay. So if sigma is a constant, then if h is a constant which is not 0, which is usually called a CMC hypersurface. So minimal surface is always a critical point for the area functional, and the CMC hypersurfaces are critical points of the area functional under some constraint variations, under these variations that I have to require. So this equal to 0. This aspect is volume preserving, under any volume preserving variations is a critical point, then this is a CMC. Okay. So now let's compare what we have on the board and this new concept. We have a variational invariance called the volume spectrum. We also have the half volume spectrum. For the volume spectrum, you have a sequence of numbers that's diverging to infinity. Each of them is defined as a min-max value for the area functional. So it's natural to ask whether those critical values are related to their critical points, which are minimal surfaces. Well, there was a conjecture by S.T. Yao in the early 80s. He conjectured that every closed three manifold contains like infinitely many closed minimal surfaces. He only says immerse. When he makes a conjecture, of course, we haven't know anything on this board. He makes a conjecture just by, in my understanding, comparing to what was known for closed geodesics on a two-sphere. So it's now already a theorem. There was like two major breakthrough related to that, one by Marquez Neves and the other work by Antoine Song. So they make the conjecture to be a theorem. So they show that any closed manifold of dimension between 3 and 7. So this is a regularity concern. In higher dimensions, you may see singularities. So every such manifold admits infinitely many closed embedded minimal hypersurfaces. So the volume spectrum, the PVs played an essential role in the resolution of this famous conjecture. So behind everything was this so-called Almgren-Peace theorem. Almgren-Peace min-max theorem. So roughly speaking, because that omega p is written as an infimum over a maximum, it's a saddle point construction. Roughly, the theory says that this is related to this is achieved by area of minimal hypersurfaces. Of course, to prove the existence of infinite many, there are some obstacles, key challenges there. For instance, minimal surfaces produced by the theory may be counted by integer multiplicities. It's kind of like when you produce closed geodesics, you can go around the geodesics many times. So I'm not going to really dip into the history. It's a long history there. So what I wanted to ask is, what do you think is the natural analog of the theorem in the CMC category? What is the, if there is a single CMC analog of Yau's conjecture? Yeah, I have been interested in this related question for quite a while. And one thing in my point of view is that I try to convince you by what I wrote on the board. This conjecture was solved by showing that this volume spectrum was realized by minimal hypersurfaces. Then you might imagine I have another sequence of invariants, whether we can try to show that these new invariants are achieved by critical points. Because in my definition of this new invariant, I use hypersurfaces which bound half of the volume. So if you consider variation in this space, you'll naturally encounter volume-preserving variations. So the critical points you produce can only be constant mean curvature. It may not be minimal. So let me state a conjecture that Liam and I made, and I will tell you what we can prove regarding this conjecture. So we conjecture that every closed manifold of dimension between 3 and 7 should admit infinitely many, we call them half volume CMC hypersurfaces. So here by half volume, it actually means that it bounds a domain which equals half of the volume. So here, so sigma is a boundary. We do not require them to be connected anyway, such that this volume is the number h. I wrote over there, and the mean curvature is constant. Okay, so this is what we mean by half volume CMCs. Maybe at this point, you can just say that this is just an analog coming from the method. Let me just, before I talk about what we can prove regarding this conjecture, I want to motivate you a bit more why we think this should be the right conjecture regarding CMCs. Okay, so to do that, let me mention a related problem. In this problem, we just try to search for hypersurfaces which are critical points for the area functional with a fixed volume. Say this is a fixed half volume. You may also ask me, what about other volumes which are not half of the volume, right? But before that, I try to answer this question, I want to talk about a related question. The question was, instead of searching for CMCs with a fixed volume, I want to search for CMCs with a fixed mean curvature value. Search for CMCs whose mean curvature is given by a priori number. Okay, so for every number C, I search for CMC whose mean curvature is given by a constant C. So this time, we still try to understand using a variational point of view, but we should consider for a different functional rather than the area functional. We should look for this Lagrangian multiplier functional. So this time, I should apply to omega rather than the hypersurface. It's the area, it's n-dimensional area of the boundary minus constant C times the volume of this omega. Say if this is n plus 1 dimensional manifold, so this is my omega. This is a boundary. Okay, I look for the area, subtract C times the volume. You imagine this is still the area functional, but I added a Lagrangian multiplier. We do Lagrangian multipliers a constant times some other constraint. Let's do the first variation argument as in this picture. If I'm taking the first variation for this new functional under vector field, the first term of the area term still gave me the integral of the mean curvature times x dot n. And the second term is a volume. If you take the first variation of the volume, it reduces the integral on the boundary of the speed. Okay, let's try to manipulate this integral. It becomes this mean curvature minus a constant times this normal speed. Okay. So therefore, it's easy to see that if I want to prescribe the mean curvature, I should look for the critical point of this functional. So sigma is a critical point of this functional if and only if so the mean curvature of sigma is equal to C. So it looks for this functional. So a few years ago, also using the idea of min-max, Jonathan Zhou and I proved that every closed manifold of those low dimensions admits at least one closed hypersurface whose mean curvature is C. So I'm not going to write it down. The idea was that you try to look for the critical point for this functional, but the functional has trivial critical points, which are the empty side, whose boundary is empty, and a total manifold, whose boundary is still empty. So empty are two critical points of this new functional. So the trivial critical point doesn't exist. You should look for the saddle points. So we use a mountain path arguments to show the existence. So people may ask, like, whether you can prove the existence of infinite many for this problem. For that one, I'm not quite sure. But there was a conjecture by Arnold. So he can conjecture that every two sphere endowed with the Riemann metric, so it should admit, I should say for every constant kappa, it should admit at least two closed curve of constant geodesic curvature. So let me see gamma 1, gamma 2, whose geodesic curvature is the kappa. So this is the geodesic curvature. Okay. So Arnold also called them like magnetic geodesic. There were some experts in the audience. My understanding is that this is still open for the general case, but there are many, many partial results. So if you compare these two problems, I think a natural question is to ask is, I didn't see anyone summarizing that, so I summarized it somewhere. I call them the twin bubble, so it's a similar one. I say for every C positive, a manifold, say in low dimensions, so admits, so at least two closed hypersurface whose mean curvature is C. There were some, I guess some heuristic suggesting that, for instance, in any rotational symmetric manifold, there are at least two CMC hypersurfaces over there. Or if you think in the Luchternik-Schneermann or Morse point of view, the cycles, if you think the cycle space sort of as S2 also, it should have two critical points. I don't think any of them is really a solid reason. Okay, so let's put things here and then compare that conjecture with this conjecture. So Yale's conjecture asks the existence of minimal surfaces, which can be viewed as Yale's conjecture asks for CMC surfaces whose mean curvature value C equal to 0. So if you think of the mean curvature C as all real numbers, it goes, this is 0, it can go to plus infinity, it goes to negative infinity. So Yale's conjecture tells you that exactly at the middle, you expect to see, you already know this is true, infinite many closed minimal surfaces. So this is a prescribed mean curvature problem. Now let's imagine the prescribing volume problem, prescribed in enclosed volume. So the enclosed volume also has a spectrum. That is from half of the total volume into the, this is 0 volume, half volume, total volume. So my understanding is that at the middle of them, that's analog of h equal to 0. For all hypersurfaces which enclose half of the volume, you expect to have infinitely many critical points for the area functional. Away from the middle spectrum, you expect to have one each. They all have the same mean curvatures. So that is the number 2. So we also made a conjecture for prescribing other volume CMCs. We think the number may be 2. Okay. I hope this is like a stronger supporting argument why we think that's the right conjecture. So if you think of this as which sits in the middle of this problem, then that conjecture sits in the middle of prescribed volume CMC problems. And of course, we have another technical supporting, that is we have this new invariance, which tells us that there is enough topology to run the variational arguments. Okay. Okay, suppose like you're convinced that this is the right problem to do, then I'm going to show you what we can do for this new problem. So we try to develop a similar theory as this Armstrong Peace theory. This is a theorem drawn with also Leon Mazurovsky. So we show that in the archive paper we restricted to n less equal than 5, but there was new preprint on the archive in the last 1 or 2 weeks. They deal with a lemma that extends to dimension 6. I think we can do up to dimension 6 now. So in these dimensions, we were able to show that, okay, also for generic, I'll tell you what does this mean soon. For generic Riemannian matrix, so there exists infinitely many half-volume CMC hypersurfaces. So in dimension 3 to 6, for generic metric, this is smooth generic metric, I need to tell you when I go into the proof, what does this mean? There always exists infinite many half-volume CMCs. Moreover, we were able to show that for generic metric in those dimensions, each omega tilde p, this is a half-volume spectrum, is realized as the area of some smooth n-dimensional hypersurface. So these are half-volume CMCs. We were able to show that each of the spectrum was realized by the areas. If you compare, we actually proved in the half-volume setting Armstrong Peace type theorem. with a stronger result. So there I didn't go into the details. The general theory produces minimal hypersurfaces counted with integer multiplicities. And I was able to resolve a conjecture by Marquez-Neves, which says that for bumping metrics, those multiplicities are always 1. So for generic cases, in this setup, we know that each volume spectrum can be realized as the area of a closed minimal hypersurface. And now we're able to show that this is the case for the half volume setting. Okay. Our method also gives some partial results regarding that conjecture. So let me introduce that result. So let's go back to this conjecture. I want to call them a good name. I call them a twin bubble conjecture. Even though I'm not sure whether it's true. What we can show for the twin bubble conjecture, so we were able to show that in between dimensions 3 and 7, so any such manifold with a generic metric, we were able to show that either the first case happened, that there exists like infinitely many, I should say for every C, there exists infinitely many CMC hypersurfaces, which means that those hypersurfaces have a constant mean curvature C for this given C, or there exists infinitely many half volume CMCs. So whose mean curvature is strictly less than C. So either we were able to solve that for generic metrics. There exists, we show infinitely many. So even I conjecture is greater or equal than 2. Or there are infinitely many half volume CMCs. I still have some time to introduce some key technical ideas behind the two theorems. They're related. Let me first talk about the first theorem, and then I'll tell you how to make a variant of the results to the second one. Okay. So to prove the first theorem, the existence of infinitely many half-volume CMCs, or to show that each half-volume spectrum are realized by half-volume CMCs, we actually consider the area functional restricted to all of those half-volume cycles. So note that these are all subsets whose volume equals half of the total volume. So I would say that having a variational theory directly working on this space is pretty hard, because if you do any variational theory preserving these volume conditions, you have to look for these vector fields which preserve the volume. A natural kind of choice are these divergence-free vector fields, but these vector fields are not easy to manipulate. So I would say it's very hard to directly work on this space due to technical reasons, many constraints. So what we do is to do a panelization or relaxation method. We consider like this Ginsburg-Landau type thing. It's Ginsburg-Landau type, not exactly their things. So we try to relax this into the total boundary space. So note that these are the space of all boundaries quotient by Z2. So but if we work on all boundaries, we lose this half volume constraint. So we added them back. So we call them the EK functional. The EK functional are the area of the boundary plus a panelization term. So K is a number. So we panelize how the volume differs from half of the volume. So K are all integers. We will eventually let K go to infinity. Suppose I were able to produce a critical point for this functional, which seems to be easy because the total space has no constraint. If I let K go to infinity, if everything is bounded, that will force the volume converting to half of the volume. So I call it a Ginsburg-Landau type panelized functional. But there were new challenges for this functional. That's because this panelized term it's unlike of this term. So this is a Lagrangian multiplier. It's very different. Let me say a few words here. So if you work on this Lagrangian multiplier term, they are both local functionals. By local, I mean first local versus non-local. So by local functional, that's this AC type functional. So this is an EK type functional. By local, I mean, so suppose I have two subsets in my manifold. So I do a perturbation here. I do a perturbation there. The total effect is the sum of the effect applying to each of the subsets if they're disjoint. That's called a local functional. So this is a non-local functional, which means that if I perturb here a little bit, perturbing there a little bit, the total effect is not the sum of their local perturbations because of this square term. So we have to develop like new technical tools to deal with that. So fortunately, we are able to produce a new theory telling us that we can do that. So the theorem says that if you do any min-max construction associated with this EK type functional, so this is given by the following, given by a pair. One of them is still a Cartier polyset. The other one is a varifold. So if you're not familiar with this notion, this varifold can be understood as a generalized n-dimensional hypersurface. N-dimensional hypersurface we usually call them integral varifolds. It's a Lipschitz submanifold patched together. So we show that the min-max is realized by a pair. The reason is because so if I call this a min-max value, so this value is achieved by the total mass of the varifold, so plus that term. So the volume term is still there. It's still counted by Cartier polyset. But these boundary measures are now counted by a total measure of a varifold. The reason is because at this stage, we still allow multiplicities. So like you can have several layers of multiplicity. One hypersurface is collapsed down together. So this boundary layer will have a higher multiplicity. And we were able to show, if you really do a so this V is a sum of some minimal surfaces. So this lambda I is the boundary of omega. These have CMC, so these are minimal surfaces. We call them minimal bubbles. And the mean curvature of this guy, if you do a calculation, it's easy to see that equals 2k times omega minus h. I think in this case, I may have minus sign. So we were able to produce such a theorem. It's not very satisfied now. It just roughly tells you that if you can realize a critical value of this functional as some area of minimal surfaces counted with multiplicities together with some CMC surfaces which bound that kind of volume. So if you let k go to infinity at this stage, I'll show you what's happening. So let k go to infinity. So now I actually need to give each of them a k. Let k go to infinity, so this LK goes to eventually this omega q to p. So this Vk, this varifolds will go to V infinity. So using compactness theorem for minimal surfaces and CMC surfaces, so this is integer multiple of some minimal bubbles plus some CMC parts. And the gain we have here is that in this case, so this is the boundary of some omega. So this omega has a half volume. And the mean curvature goes to some number. But actually, this comes from the fact that this thing are uniformly bounded. So this is uniformly bounded. So that tells us that volume will be false to this half volume. It's not a satisfying theory at this stage because there are minimal bubbles here. So we cannot really show that these half volume CMCs have their area diverge to plus infinity. So we actually have to do a variant of this theory. To go around that, we adapted this idea that I used in my proof of the multi-prism conjecture. We consider a F functional. So F functional has two parameters, k and delta. So here we should choose a generic smooth function and fix it and look for the functional which is the ek functional. Plus or minus, depends on what you want, an integral of this h. So this is a Lagrangian multiplier term. So I added my non-local functional by a Lagrangian multiplier term. So this Lagrangian multiplier term plays a role that if you have some minimal surfaces, so it actually tries to automatically split them off. So minimal surface, you split off a little bit. So then the theorem becomes, so if I run a min-max, so it depends on two parameters. So this is min-max of this new functional. So the value is also realized by a couple, a pair, Cartier polyset of varifold. So this time, this LK delta only consists of this next parts. So the union of lambda I are boundary of omega. And so this varifold is given by lambda I. And the mean curvature still satisfies the same thing. But this time, the mean curvature is slightly different. It's delta H minus this 2K star. Okay, so that's this theorem. So the theorem by adding this term has a similar flavor as in the minimal surface case that actually perturb this minimal slice away. You only leave with multi-prism boundaries. Okay. So now I have to let delta go to 0 and then let k go to 0. But there's still possibility that when they all go to 0, it collapses to minimal case. Let me just say how to rule that out. We do the following two limits. So then things converges to also a pair. So there are two possibilities. One possibility is that these are the minimal surfaces. They're all minimal bubbles. Now the things we can actually rule out is that if you take this to infinity, you get minimal bubbles together with CMC components. But in this case, we can either get all minimal bubbles or they are all non-trivial CMC parts. So in this case, some subset of them is a boundary of a set with half of the volume. And so in this case, we can actually prove genericity theorems showing that we can show that for generic smooth matrix, no half volume minimal surfaces exist. There's no half volume minimal surfaces. So this case never happened for generic matrix. This is how we mean by generic matrix. You can imagine that if you, and a matrix, if you have a minimal surface which bounds half of the volume, but you're perturbing one side a little bit, the volume increase, the volume decrease. It's no longer half volume CMCs. You have to do this in countable many times. You can show that. So we only have the second case left over. We have They're all half volume CMCs. So here I want to highlight something. So in this case, when I let k go to infinity, I have to make sure that this is uniformly bounded. So it depends on k and dirt. No. So I have to show this is uniformly bounded. So for that reason, I have to use a classical theorem by a list of authors. Let me read the author's name. I have to use classical results by Albert Nelly and Rosenberg. So they had a paper solving the Docamo problem, where they solved the Docamo problem. It's an E, right? Docamo. So Docamo problem asks like when a complete CMC surface is always compact. So they were able to show that between dimension 3 and 5, that's always compact. And there were some recent preprints which appeared last week or week before. They extended this Docamo problem to dimension 6. So our results should also hold in dimension 6. So the idea was that if this was not, in this case, delta is already gone. So we have CMC surfaces. If they're not uniformly bounded, by doing a blow-up arguments, you have many small components. So since each of them has bounded, are closed, they have bounded diameter. So essentially, if this blows up, then in the manifold, what you see is many, many small balls. So by using isoperimetric inequality, you can count that. So if you have many, many such balls which bound half of the volume, their boundary area will be super large. But they have uniformly bounded things because they convert this to omega p anyway. So that is the first theorem. I'm almost out of time. Let me use a couple seconds to see how we can use this method to deal with this half volume case. Essentially, if I want to talk about this existence of more than one CMC surfaces, I have to consider, let me just squeeze the space and just talk about here. So given a Cartier polycide, we not only need to consider AC of omega, so which is boundary omega minus c times the volume of omega. We also have to consider that measure c times this complement. So we want to look at the maximum between these two. So there was a heuristic that reason that forces us to consider the maximum between the AC value in this side or in the other side. So you look at this side or look at the other side. So if you rewrite this, this will be the area of omega plus or minus, I think it's plus. The absolute value between the total volume minus h plus minus another constant. So literally, our method to consider this twin bubble problem is to consider this functional. So this functional is actually not smooth along these half volume surfaces because heuristically, this functional, we call it A tilde c. There's a c here. This is another some constant. So this A tilde c functional, if you look for this graph, is as follows. So those are all half volume surfaces. It's something like it's something like that. So it's smooth away from this tip. I can do variational theory. I can obtain smooth critical points away from the tip. But I hit the trouble there because intuitively this functional is not smooth there. That's why Liam and I consider variational theory inside the space and obtain that analogs. So what we do is that we can do a natural regularization here with this new technique. This new technique deals with these non-local functionals. So we can change this part into c like epsilon squared plus square root of omega minus h squared. Oh, sorry. So we can deal with this type of functional now. This is a new theory. And we can produce a critical point there, and then let this epsilon go to 0. So there are two possibilities. One possibility is that if they stay away from being half volume, it's easy to see that the mean curvature will become c. But if they convert this to being half volume, the tangent can be any number between 1 and c. So that's why we can only produce half volume CMCs with mean curvature bounded by c. I'm sorry, I should stop here.